Welcome to the Explainer. We've got a really fantastic journey ahead of us today, exploring the fascinating world of Class 10 real numbers. We're going to start by looking at the fundamental DNA of numbers themselves, and by the end of this, we will literally be catching abstract mathematical concepts in a lie. I'm so excited to guide you through this, so let's jump right in.
But first, think about this for a second. How can you mathematically prove the impossible? It sounds like a total paradox, right? Well, today, we're going to look at how we use a highly structured, almost detective-like logic framework to prove the existence and the nature of things that seem absolutely impossible to measure.
Here's our roadmap for today's Explainer. First, the DNA of numbers. Second, decoding HCF and LCM. Third, meet the irrational numbers. Fourth, proving the impossible. And finally, the decimal destiny.
All right, let's start things off with Section 1, the DNA of numbers. So, the fundamental theorem of arithmetic, it basically tells us that every single composite number can be uniquely expressed as a product of prime numbers. Think of prime numbers as literally the DNA of mathematics. Just like genetic code, you can break down any number into its prime factors. Take the number 36, for example. It's simply a unique combination of 2's and 3's. Specifically, 2 squared multiplied by 3 squared. And you know, no matter what order you multiply them in, that specific combination of primes is the unique genetic signature of 36.
Moving right along to Section 2, decoding HCF and LCM.
The crucial trick here is understanding exactly how we handle these prime factors. To find the HCF, or highest common factor, you're really just looking for common ground. You only look at the prime factors that both numbers share, and you take the absolute smallest power of those common factors. On the flip side, the LCM, or least common multiple, is a gatherer. You look at every single prime factor involved across both numbers, and you take the greatest power of each. It's this beautiful contrast, really, between finding the simplest shared elements versus gathering the maximum potential of all of them.
But hold on a second. If we have the highest common factor on one hand and the least common multiple on the other, what's the secret link between these numbers? Because there is a hidden relationship here, and it's incredibly powerful.
Here it is. I absolutely love this. It's basically a mathematical cheat code. If you take the HCF of two numbers and multiply it by the LCM of those same two numbers, it will always, and I mean always, exactly equal the product of the two original numbers themselves. This is a hugely frequently tested concept and just a fantastic shortcut, especially when you're tackling multiple choice questions.
Let's look at a concrete example using the numbers 26 and 91 to actually see that cheat code in action. So, the highest common factor of 26 and 91 is 13. Their least common multiple is 182. If we multiply our HCF of 13 by our LCM of 182, we get 2,366. Now watch what happens when we just multiply our original number A and number B. 26 times 91? It also gives us 2,366. It balances out perfectly every single time. How cool is that?
Let's shift gears into Section 3, meet the irrational numbers.
Irrational numbers are the absolute rebels of the math world. By definition, they completely refuse to be expressed as a simple fraction, p over q. When you look at them as decimals, they feature non-repeating, non-terminating expansions, meaning they just go on forever without ever settling into a predictable pattern. Famous examples, the square root of 2, the square root of 3, and of course, pi. They just won't conform to that neat simple fraction lifestyle that rational numbers get to enjoy.
So what actually happens when these rule breakers interact with our well-behaved rational numbers? Let's rapid fire through these properties. If you add two rational numbers or multiply two rational numbers, the result safely stays rational. No surprises there. But if you add a rational number to an irrational number, the result becomes irrational. The exact same goes for multiplication. A rational multiplied by an irrational usually gives you an irrational result. It's almost like the irrational number infects the equation, pulling the neat rational number right into its chaotic, non-terminating world.
That brings us to Section 4, proving the impossible. Okay, let's really dive into this logic. We use a method called proof by contradiction. Think of it like walking down a logical staircase. First, we assume the suspect's alibi is true. We assume the square root of 2 is a rational fraction p over q, where p and q share absolutely no common factors. Step 2, we square both sides and rearrange things to get p squared equals 2 times q squared. Because it's a multiple of 2, step 3 proves that p must be an even number. Now, if p is even, we can substitute that back into the equation, which leads us straight to step 4, proving that q is also an even number. And boom, there is our step 5, the contradiction. If both p and q are even, they share a common factor of 2. That totally destroys our very first assumption. The alibi falls apart, and we've successfully proven that the square root of 2 is in fact irrational.
Watch out for a huge hidden trapdoor here, though. Theorem alert. When you're executing this proof on an exam, you make a pretty big logical leap from saying p squared is even to stating p is even. Students lose marks here all the time. You absolutely must explicitly state this underlying theorem to justify your logic. If a prime number p divides a squared, then p also divides a. Writing down that single sentence is what secures your full marks and proves you truly understand the mechanics behind the proof.
Finally, Section 5, the decimal destiny. The absolute crucial point for determining a fraction's decimal destiny is this exact formula: 2 to the power of n times 5 to the power of m. When you break a denominator down to its prime DNA, this specific combination of 2's and 5's is the ultimate gatekeeper for whether a decimal will cleanly terminate or repeat forever.
Let's see this gatekeeper rule in action. If you have a fraction like 17 over 8, you just look at the denominator, 8. Its prime factorization is 2 cubed. Because its prime factors are only composed of 2's, which fits perfectly into our gatekeeper formula, we know for a fact it'll be a cleanly terminating decimal. But look at the fraction 64 over 455. The prime factorization of 455 is 5 times 91. Because a prime number other than 2 or 5 has sneaked into the denominator, it is destined to be a non-terminating, repeating decimal. The prime DNA of the denominator tells you the entire story instantly without you ever having to do the long division.
Before we wrap up, take a look at this exam day cheat sheet. It's a fantastic visual summary pulled directly from our sources that outlines the properties of rational and irrational sums, products, and the core summaries of the fundamental theorem. Honestly, this is the perfect moment to pause and take a screenshot for a quick review right before your exams.
We've covered some incredible ground today, from the prime DNA that builds every single number to using the brilliant logic of contradiction to prove irrationality. But, it leaves you wondering, if prime numbers are the fundamental genetic code of mathematics, what other seemingly impossible truths are just out there, waiting to be caught in a contradiction? Keep that curiosity alive, keep looking for the underlying structure in things, and thank you so much for joining me today on The Explainer.